All right, so let's get started again with a final stretch today. So, routing and forwarding here. These are two terms which are typically sometimes used interchangeably, but should one be careful, they do two different things. So let's try to explain this. So in this example here, we have a local area network here at Alice's home place. So this is at Alice and this is at Bob. There's some switch here, so this is a local area network. We have a router, we have a wide area network and another router and then a switch and Bob's place here. Okay, so when everything starts here, we need to assign network addresses here to all of these. So assuming that things have been powered up and configured and whatnot, and here we have IP addresses for all network interface cards that will be involved into this, right? So we have a bunch of these IP addresses. Now, suppose how does this work now when Alice wants to transmit a packet somewhere? So Alice's IP layer would like to transmit a packet with a certain destination. So if it wants to go to, and to do that, Alice's computer use a IP routing table. Okay, so this is the, yeah. And the content of this is it's a table where you have a column for the destination IP, next hop IP, and the interface, which one should use. And the content of these are all in terms of IP addresses. So the interpretation of this is that if Alice would like to send an IP packet to NB, it should then transmit the packet. The next hop of the packet should go to N1. Okay, and N1, that IP address is reached by using the interface NA. So this identifies the network interface card. We might have several. So for instance, this laptop has a wired Ethernet, has Wi-Fi, and I could have a cellular modem or something in this. So I have several networks attached to this one at the same time, and so multiple of these network interface cards here. But I know that I can find a network interface card by an IP address. Okay. So it's not. Maybe it seems a little bit odd that we specify the interface here in terms of its IP address rather than its physical address. But remember now that this is all in the IP layer. We do this, so it's more convenient to work maybe with the IP addresses. Okay. So what happens now is that if a packet needs to go to Bob, okay, Bob has IP address NB. Alice have no idea where Bob is located. Okay, but Alice's table tells me that if Alice would like to send something to Bob, you should first send the packet to N1, which is the IP packet of router number 1. The IP address of router number 1. And it can reach N1 by using the interface NA, which is this interface, which indeed, through the switch, is connected to the router interface that has IP address N1. Okay. So that's what we read here. Going to NB, then send it first to N1 using the interface, the local interface, which has IP address NA. Reasonably clear? Okay. Now, the packet has now gone from here to here. Okay. So we have here that okay, the packet, what is the packet structure? The packet structure is actually like this. It's the source, and then it's the destination, and then it's data. This is the IP packet. So the first thing to do is then to inspect the destination, read off this line, and then figure out, okay, we should send it to N1, and then using interface, N1 using the interface NA. And then the packet has now gone here. At this point in the diagram, the router would receive this packet. It will look at, okay, it comes from NA, it should go to NB. All right? So the router then looks at NB and finds a line in its routing table that tells us, okay, it should be sent off to a node which has network address N3, IP address N3, and we can reach that by going out on the interface, the local interface that has IP address N2. Okay, so it should go out this interface, not this one, and not, oops, sorry, and not this way, right? It should not go out that way. It should go out this way. Not that way, but this way, because that's what the table told us. Okay, and then the IP packet would then go over here, and the process of going from here to here, this is called forwarding. Okay, the IP packet has now reached router number 2. Router number 2 also have an IP routing table, and it looks then at the packet. It still has destination address NB, and therefore it figure out, okay, the next hop should be to NB, actually the destination, and this is reachable by the local interface N4. So we have here N4, and we know that we can reach NB. And then the packet is then goes over there and out this link. And this is now again some forwarding. And then it reaches its destination. Okay. So to find its way through the network, none of the intermediate node here knows the complete path. It only knows the next hop. But the combined effect of all of these routing tables defines a path through the network. And the process of populating these tables in a way such that they are consistent and efficient is called routing. Okay. Fill out tables. That is known as routing. Okay. So there is a routing protocol whose purpose is to figure out what should be the content of these tables. Forwarding is what's done by the router. It's the process of moving a packet from an input port to the appropriate output port, which is specified by the forwarding table. Okay. Now, we will be sloppy and call this routing anyways, right? But if one should be careful, these are the distinctions. Forwarding is the action of moving from input port to output port. Routing is the process of filling out the routing tables. Sorry, the forwarding tables. Okay, any questions so far? Yes?
Are these tables like huge since there are multiple?
Ah, that's an excellent question. So how big are these tables? And if one would have an entry for each IP address, okay, then we know IP version 4 has 32-bit addresses. Okay. How large would the table be then? How many rows?
2 to 32.
Yeah, 2 to the 32, which I believe is about 4 million entries. Okay. I mean, it's sort of doable, but do you really want to have that in each of every device? So no, you don't have that. And then we know that there is, or maybe there is an IP version 6, which is the successor to IPv4, because we're running out of addresses here. It has 128-bit addresses. And 2 to the power 128, I don't know, but it's 10 to the 12 or something like this, I would think. That is not feasible. Okay. And the thing that saves us is the hierarchical nature of IP addresses. An IP address is hierarchical. And we can think of this almost as a, let me do an example to explain what I mean. That if I would get an envelope for somebody, right? So it goes to me, so that identifies me, but I live at some street, at some zip code, at some city, right? So when the mail office gets this from the sender, it would look at, okay, the zip code and city. Then if this mail was sent, say, from Stockholm, it would put it in the Gothenburg bin, right? So it only needs to know, it can make a forwarding decision based on parts of the address. And that keeps the table size down quite a lot. Then when it reaches Gothenburg, it can look at the street name and then figure out, okay, it needs to go out with this mail delivering person, right? So it's put in another bin, and then the mail delivery person would put this in the mailbox, and then it's up to my family to sort out who's going to get the last one, right? Is it to my wife or my kids or to me? So this is a hierarchical address scheme, and it's great to keep the size of the forwarding tables low. The link layer address, however, is flat, so it has no hierarchy in it. But that's fine because there are not so many nodes attached to a local area network, so that's fine. So you can keep tables small. But that's a great question. I should have mentioned that. Anything else? Any other question at this point? Okay. Okay. So, sorry for the mess here. So, forwarding is the process of moving a packet across a router, from one input to another output, and it's defined by the forwarding table. Routing is the process of populating the forwarding tables, and that's done by the network protocol or manually. You probably want to automate this, right? And the forwarding table defines a path or a route through the network, and these are typically dynamic, so they change over time. So every now and then one updates this because nodes come and go, links come and go, and so forth. All right. Now, yes?
Just here, so every router has one of these tables.
Exactly. So each node, so the computer also have a routing table. Sorry, forwarding table. You see, I mess up this routing and forwarding already. Yeah, but that's true. And they are different. Okay, so the address resolution protocol is the protocol that translates between IP addresses and link layer addresses, and this is needed, as we will see here. So, to transmit an IP packet over a link, the IP destination address needs to be translated to the corresponding link address. And why is this? Well, it's because if I'm IP, I know where my IP packet should go to, but I need to instruct the network layer to what is the address of the next hop I want this packet to go to. And the link layer only understands link layer addresses. It doesn't understand IP addresses. So I need to translate my IP address into a link layer address before I push it down. Or when I push down the IP packet, I also need to augment that with where it should go to. And that address has to be link layer address, because that's what the link layer understands. It doesn't understand IP addresses. Okay, so so it works like this, that the IP, okay, suppose an IP packet needs to go from system 1 to system 2. Okay, so the IP packet itself will have the format. It comes from system 1 and it needs to go to system 2, and there is some data. This is the IP packet. Okay. So the network layer here is IP, but it wants to use a link layer below it, because that's what layers do. Okay, and suppose this link layer, it could be in Ethernet, for instance. Okay, so the system number 1 has a network address N1. It also has a link layer address L1. Okay, it has, you know, an IP and a link layer address to this network interface card. And the IP layer here, in the beginning, doesn't know what other nodes are attached to this local network and whether what the link addresses are. It knows, however, that there should be, in its forwarding table, it knows that there should be a system which has network address N2. Otherwise, things will fail, right? But it is here, right? So the system number 1, the IP in system number 1, needs to translate N2, which is the destination address, to the corresponding link layer address, which is L2. And it uses ARP for this. And ARP, what it does in system 1, it broadcasts a request basically asking what link layer address of what is the link layer address of the node with IP address N2. Okay. And then the ARP request is processed by all the attached system to the local area network, and the system with the requested IP address replies and say, hey, it's me. And it says, and it sends a response to system 1 and say, the node with IP N2 has link layer address L2. So in pictures, we have a number of systems all attached to this local area network. First thing to do is that ARP at system 1 is asking the network, hey, who of you guys has link layer address N2? So it sends out this red broadcast, and since it's broadcast, it goes through and it's processed by all link layers as a valid address, and then sent out to the corresponding ARP protocol entity here. So now a request has been sent from system 1 to system 2, system 3, and system 4. All of the ARPs here, they know their own network address. So system 3, for instance, see, okay, so somebody asks for who has network address N2. I don't have N3. I don't, so this is not for me. And the same thing for N4. But N2 says, hey, somebody is asking me for my link address. So then I will answer that by sending a message back to ARP here. Okay. So by doing this, we send an ARP request and an ARP response. Now IP in system 1 knows that the link address to the system which has IP address N2 is L2. Okay. So this is why you sometimes need this broadcast address. Okay. But in the return, since ARP here has already knows from which link layer, it knows the link layer address of the querying system, so you can send unicast back here. It doesn't need to send broadcast in the back in the response here. So any questions on this? Okay. So this is almost like DNS, right? We want to translate from one addressing format to the other. So now system number 2 also know the link layer address of the next hop, of the system that needs to go to the next hop. Okay. Okay, so again, we have this example here. We have Alice, we have Bob. All network interface cards have a network address and a link address. And we use ARP to translate between these. So now, if Alice wants to send a message to the first router, remember that Alice has looked in her forwarding table and figured out, okay, the next hop is to a system which has network address N1. So Alice's IP layer gets some data from above, and it also gets the final destination, which is Bob's IP address. Okay. So what is then the network layer going to do with this? It will then look at NB, okay, in its forwarding table, and then figure out, okay, the next hop is to N1. So now IP at Alice's site, Alice's computer knows that the next hop is to N1. But where is N1? Where is the link layer address of N1? This is not known yet, but we use ARP. What happened now? We ask ARP to figure this one out for us, and then the router answers back to Alice's computer. Okay, you want to go to link layer to a node with link layer address L1, and then this is then fed back here. Okay, so here's the boundary between the network layer and the link layer. So now the link layer can be activated. Oops, that was a bad line. Okay, so what happens now is that the network layer can encapsulate the data with its source address, destination address, and push that down to the link layer together with the link layer address. The link layer address is needed for the link layer to know where should this packet go to, because the link layer is not allowed to look at the IP addresses, because this is data, it's payload, right? So it gets the link layer address here, and the link layer then encapsulates this into a link layer packet, which is the service data unit it got from above, which consists of, which is an IP packet, but then it attaches also its destination address and source address. Okay, so the link layer works on these addresses, has no understanding of these addresses, and doesn't use them. Okay, and then it can then push it down to the physical address, and then it's transmitted with a waveform to out on this link. So any question on this process as described now? Okay. So we see here we do encapsulation, right? We go to data, we add some header, and then this is then seen as a payload for the layer below, and we add some header to this. Now, what we didn't mention explicitly before is that sometimes you have to instruct also the layer below where it should go with an address that that layer understands. In this case, a link layer. And the link layer we got through ARP. Link layer address we got through ARP. Now, there's a little bit of a quirkiness here also that, okay, and then this goes like a waveform to router 1. And that is for some reason, the order of destination and source addresses in IP is reversed from Ethernet, right? So it's actually that here's the source and destination, here's the destination, here's the source. So it's actually not a typo in the slides here. It doesn't matter in which order it appears as long as we know what we're doing. Okay? So now we have described the process from when Alice's side here, where it got the data and the destination IP, and now this is translated to a waveform, which is put out on the right output port. What happens in router 1 here? Okay, so now we need to do routing. So the first thing that happens is that we get the signal from Alice's, from whatever cable that came from Alice. It's hooked into our router here, right? So the signal comes from Alice, comes up here. And then we do decapsulation. It goes up into the data link layer. The data link layer then looks at the data it gets from the physical layer and see, okay, there is a match between the link layer address. This link layer address is actually for me. So I need to process this frame. If the link layer address is not my address, I just simply discard it. Okay? Because it's not to me, right? So the link layer only processes messages which is addressed to it, either through unicast address, the L1, or the broadcast address, but not other unicast addresses. Okay, next thing to happen is that this is pushed up and it's decapsulation. We get rid of the link layer header here and push this up to the IP layer. So here's IP addresses and data. Now the IP layer here is free to inspect this. Okay, so it looks then in its forwarding table. It looks here, okay, this message needs to go to NB. So it looks in the forwarding table. Do I have an entry for NB? And yes, I do. And it should go, the next hop should go to N3. Okay, and because N3 is the IP address of the next router along the path. Okay, what link layer address does N3 have? Well, we'll ask ARP and we get it to be L3. Okay, and now the network layer here is ready to transmit the IP packet onto its, to actually do the forwarding, to move the packet from input port to output port. And it does that by simply pushing down the IP packet it just got together with the link address of the next router. The link layer then attaches the link layer address to this, and then of course uses its own destination, its own link layer address as the source address. Yes?
What was the difference between the forwarding table and the routing table?
People use the same word, and I will use it also. So it's the same. Okay, and then it's then pushed out on the physical layer, and it's output to the port, which is then going in the right direction. So it's not going up here; it's going out in that direction. And which which interface to use is actually specified by the forwarding table. I didn't mention that here explicitly. Okay. Yes.
Is there a table for link layer communication?
Could be, could be.
You don't have to use ARP every time.
Exactly, could be,
Yeah.
but I didn't include it here, so we will use ARP every time. But once you've done this, you might remember this for a short period of time at least, because it also has to time out because IP addresses could change. Right? So it's only valid for a certain time. And ARP is the safe way to figure out what is the current state. Okay, next router does exactly the same. So I only mentioned, indicated here in red, what is changed. And what is changed is that the message which is received has different link layer addresses. Okay, and then the forwarding table here would have another output. It's the next router. In this case, it happens to be the end destination, which then by asking ARP, we will get another link layer address and then put that into the packet that we transmit out to Bob. Okay. And then this goes out to Bob, and Bob then will receive something. It will go to the physical layer, up to the data link layer. The data link layer would see, okay, it's actually destined to me, so I'll accept it, and then take it out to the IP layer, and the IP layer sees, okay, it's actually for me, and then I would therefore push it up in the data stack. It should not be forwarded anymore. This is the end destination, and then we have it here. And that's it. Right. Some comments here. If you look at what is actually here, what goes up and down from the network layer, it's exactly the same packet always. Right? It doesn't change as it goes from one end to the other end. The only thing that changes is the corresponding link layer addresses. And these link layer addresses we get from the forwarding table. So it's actually virtual communication here. It's the same across this boundary here, but it's different across this boundary. And for sure it's different across this boundary. But from what goes in and out from the network layer is exactly the same. Right? Yeah, so this was quite a lot of information in a short time. Are there any questions or concerns, something that I should review or expand on? No? Because we're now in a very strange situation because I don't have more material today, and we have 10 more minutes of the lecture, so basically we can take any type of question at the moment. No. Okay, then let me just conclude by saying the material that we have covered now is quite important, like the idea of protocols, layers, encapsulation and decapsulation, and the OSI layer model and its connection to the IP model. And we did an example where we put IP and TCP IP or the internet model to work here to illustrate how things are done in practice. And I encourage you to look over the slides because it might seem simple or trivial, but it's actually quite subtle the first time you see this material. So if it seems simple to you, I would recommend that you review the material anyways and read in a book. If it seems complicated to you, of course you should do this anyways, right? But it's just a little bit of a warning here. So what we would do now in the course now, we have started from a very high level, web browsing and so forth, and then talked about link layers and network layers and so forth. Now we would look into more detail about the physical layer, how it works, what performance we can expect and so forth, and different methodologies there. And then we will work our way up in the stack again and talk about link layers, medium access control, error control, and so forth. And then a little bit on switches and so forth. Maybe touch a little bit on the network layer again before the course is, and then a little bit of security and stuff before the course ends. But tomorrow, Friday, we have a lecture where I would start on the physical layer. And then after that, you should be able to start on your project, which I encourage you to do as soon as possible. The project description should be on Canvas already now, I think. And you would get information about your group today, and then a call for a kickoff meeting for the project next week with Shuaib. Okay. Yes, a question.
Shouldn't we choose project as well?
So the question was, should we choose project also? There are 3 parts of the project, and the third part you choose, but you choose that later. So it's not open right now, because that comes after the guest lectures in these different domains, and then you can pick the one that interests you. Okay. So no need to choose anything now, but I encourage you to download the project description and start to browse it a little bit. Okay, so hopefully I'll see you guys tomorrow.